Our topic for today is basic electrical quantities. And the first quantity that we are going to talk about today is charge, specifically electrical charge. The field of electrical engineering can be vastly oversimplified by saying that it deals entirely with understanding the behavior of charge in a system. Anytime we have charge being collected somewhere, we experience voltages and corresponding electric fields. Anytime we have charges that are moving, we have currents and corresponding magnetic fields. And electrical engineering is the study of current, voltage, and electromagnetic fields. So electrical charge, a definition that we're going to have, let me do this in the same way that I've been doing it, with the name in red. I'm going to define this as the property of a particle or material that enables interaction with an electromagnetic field. I'm going to talk about the concept of electromagnetic fields a few times throughout this class. It's actually really beyond the scope of Circuits 1, but it helps in some cases to understand a little bit of the physics behind why things happen. And that's usually directly related to the presence of either an electric field, a magnetic field, or an electromagnetic field. For those of you who have taken or are taking Physics 202, effectively, we're going to hit E&M topics at roughly the same pace that you're going to hit them in that particular class, but it's going to be so small that for those of you who aren't currently enrolled in Physics 202, it's really not going to make much of a difference. Okay, so I'm not trying to convince you guys to go take a class or drop because you haven't taken this other thing. All right, so electrical charge is what's called a quantized property. Because there is a fundamental unit of charge, Q, which is 1.60218 times 10 to the negative 19 coulombs. This is the charge that a proton has. So I can call this QP. And this represents our fundamental unit of positive charge. And then the corresponding fundamental unit of negative charge, I'm going to call QE for the charge of an electron. And it is negative 1.60218 times 10 to the negative 19 coulombs, where hopefully it's fairly obvious. The coulomb, capital letter C, is the fundamental unit of charge. Right. Electrical charge is what's called a conservative quantity. And so that means it cannot be created or destroyed in a system. So if we have a closed system like an electrical circuit, the amount of charge that's contained within literally cannot change. This is going to lead to two laws that we're going to discuss on Monday's class. Kirchhoff's current law, which is effectively the law of conservation of charge in circuit form, and Kirchhoff's voltage law, which is the law of conservation of energy in circuits form, which has everything to do about transferring charge from one location in the circuit to another. So now that we have some kind of inkling of what the expectation of our understanding of charge is, we have two paths that we can take. We can talk about voltage, or we can talk about current. We're going to talk about both, but which one do you guys want to talk about first? Eric, I'm looking at you, so you're going to decide for the rest of the class. No pressure. Voltage or current? It's a binary decision. Voltage. Okay. That seems reasonable to me. Voltage, let's see, this is going to be kind of a subsection here. All right. So voltage is the electrical quantity that you're probably all the most familiar with, because I'm assuming most of you have probably had to change the batteries in your remote controls or something like that. Well, that's just replacing a voltage source with a new voltage source and all that kind of good stuff. All right. Mathematically, voltage is defined as V BA, and I'm going to explain what these subscripts mean in just a moment, is equal to the line integral from A to B of E, which is an electric field vector dotted into VL, which is a differential line element. Now, I don't exactly remember which calculus class you guys learn line integrals and all that kind of stuff in, but I do understand that maybe not all of you have had it yet, and that's perfectly okay. We're never actually going to determine voltage using this equation. It's just going to give us some insights as to the behavior of the concept of voltage. And what I mean by that is, again, for those of you who have taken or are taking Physics 202, you will quickly learn that there is a quantity called an electrostatic force, F sub E. And that is the force that charged particles exert on other charged particles. And this electrostatic force is simply given by Q charge multiplied by an electric field vector E. So what I'm going to do is I'm going to substitute this relationship into my voltage equation. And so what that gives me is 1 over Q times the integral from A to B of F dotted into DL. If we neglect that subscript E underneath the F, what does that integral represent? Force dotted into a differential line element, the force times distance. Work, exactly right. So this relationship tells us that voltage is nothing more than the work required to move charge from point A in a circuit to point B in a circuit. That's it. So we will consider voltage to be the work per unit charge needed to move 1 coulomb of charge from location A to location B in a circuit. Now we can get an alternative definition for voltage that is probably a little bit more useful in this class from this same thing if we understand the behavior of a line integral, okay? So since we are taking the line integral of a conservative quantity because it's related to charge, that means that our line integral is path independent, okay? So it doesn't matter what path we take to get from location A to location B, we're going to get the same result every time. So this is very similar to effectively measuring potential energy, okay? So if I hold this stylus at a distance of roughly 2 feet from the surface of this table, it has a particular potential energy measured with respect to the potential energy of the table. If I raise the stylus, its potential energy has increased. If I lower the stylus, its potential energy has decreased. And the potential energy, again, is measured between 2 points in the system, the current location and some reference. Voltage is the exact same type of quantity, and the line integral is what tells us that. So an alternative definition for voltage is simply the difference in electrical potential energy between 2 points in a circuit. The second definition is the one that we're going to use the most often in this class, okay? So let me ask you guys a question. How many of you have ever held or seen a AA battery? Good. The correct answer is practically all of you. What's the voltage being provided by a AA battery nominally? 1.5 volts. So what that 1.5 volts means is that there is a difference in potential energy of 1.5 volts measured between the positive polarity terminal of the battery and the negative polarity terminal of the battery. Let me ask you a different question. Does the presence of that voltage require that a current be flowing? Absolutely not. If I have a battery and I hold it in my hand, not connected to a circuit, it still exhibits a difference of electric potential of 1.5 volts, despite the fact that there is no current flowing whatsoever, right? So we can observe voltages without current flowing, okay? That's going to be something that tends to trip you guys up when we get into our circuit analysis over the next several days. So I just want to introduce that now. Voltages, we'll find, are effectively what gives the push to cause current to flow, but it doesn't necessarily mean that current is flowing. We can have a strict difference in potential without a flow of current if we have a way to store charge. Okay. All right, so voltage in our class, and this is slightly different than what you saw in your Engineering 120 series classes, it has 2 parts, okay? Voltage needs both a magnitude and a polarity to be fully defined. So what I mean by that is that if I have a generic circuit element bless you. And let's call this circuit element A. If I say that VA is equal to 5 volts, this is an underdefined description, okay? How I would correct this was I would assign a positive polarity terminal and a negative polarity terminal like so, which means there is a 5-volt potential difference across element A measured from the positive polarity terminal to the negative polarity terminal. Or another way to think about it is the positive polarity terminal is 5 volts higher in potential than the negative polarity terminal. Just like in a battery, or a AA battery specifically, the positive polarity terminal is nominally 1.5 volts higher than the negative polarity terminal. What if I wanted to know the voltage drop across this element A with the opposite polarity? What would I need to do? How many of you guys were measuring the voltage drops across resistors and all that kind of good stuff in your engineering 120 series classes and came up with a negative number? Anybody ever do that? What did you do to fix it? Flipped it. Okay, so that's exactly what we're going to do. If we flip the polarity of the terminals, we flip the sign on the magnitude of the voltage. So that means 5 volts positive polarity on top is the exact same thing as negative 5 volts positive polarity on bottom, okay? Anytime we want to make a negative voltage positive, we simply flip the polarities, all right? So this is leading me into the different ways that voltage is expressed in circuits, okay? So this is the first representation, and it is the one that I most prefer because the positive polarity and the negative polarities are clearly defined, okay? I'm going to call this the American method, because this is largely what we use here in America to describe a voltage drop in a circuit. We take that same arbitrary circuit element A. In Europe, they express the voltages like this. So they have an arrow pointing from the negative polarity terminal to the top polarity terminal, and then they give it a magnitude. I fundamentally hate this. Not going to use it, but depending on whose YouTube videos and this, that, and the other you're watching to try to make sense of the garbage I'm telling you, you might see something like this. And so I want you to understand how it relates to how we're doing things. I fundamentally don't like this because arrows to me mean current, which we haven't talked about yet, but you guys have all had classes dealing with it, okay? So this is the European method. And again, I do not particularly care for it. There's a final way to do it that we're not going to utilize a whole lot in this class, but we will on occasion. And it's what's called a double subscript notation. So in a double subscript notation, each of the terminals of the element in question is given a label. So I could call this terminal 1 and terminal 2. And so if I said V 1, 2 is equal to 5 volts. The first character in the subscript refers to the positive polarity terminal, and the second character in the subscript refers to the negative polarity terminal. So V12 would be 5 volts, V21 would then be negative 5 volts. So effectively changing the polarity means changing the order of the subscripts. For the most part, like 97% of the time, we're going to use what's called the American, or what I'm calling over here the American method. But there will be circuits / systems where using a double subscript notation will make things a little bit easier to understand. So I wanted to introduce that to you now as well. Okay. So these are the 3 different ways that we represent voltages in this class. Really the 2 different ways, because you'll never see me use this hippie European thing again after right now. All right. So what I want to talk about now is voltage sources. Okay. The different types of voltage sources that we are going to see in this class. So the first one, the one that you are likely familiar with, is this guy right here, which represents a battery. Technically, this depiction represents a single cell battery, where the long horizontal line corresponds to the positive polarity terminal, and the short horizontal line corresponds to the negative polarity terminal. Okay. This is the symbol that was used to generate voltages in practically every circuit that you dealt with in your engineering 120 series. My preference is to use this representation. This is a generic DC voltage source. I like this one because the positive polarity terminal and negative polarity terminals are clearly defined. Positive polarity terminal is the one with a plus sign. The negative polarity terminal is obviously the one with a minus sign. There is no ambiguity. There is no way we could accidentally confuse it with a capacitor, which is represented in schematic diagrams by 2 parallel lines. Okay. So this one right here is the one that I prefer to use. Later on in this class, we will use this guy. It's effectively the exact same symbol, except that there's a little squiggle in the middle. And what that squiggle represents is that the voltage is time varying. So this will be called an AC voltage source. These 3 sources are what are called independent. Sources. And what an independent source does is it supplies a fixed amount of a quantity regardless of what else is connected to. Okay. So a 5-volt battery in our class supplies 5 volts if it's connected to nothing or if it's connected to lots of other circuitry, lots of other components, does not matter. The voltage for an independent voltage source is fixed, and the current is whatever it needs to be. Okay, so the voltage is fixed, the current has an undetermined value, which has nothing to do with the voltage being supplied. Now we have two more that I'm going to put over here to the right, and you guys are going to hate these. Just throw it out there. So this first guy that I'm writing here or drawing here is what's known as a voltage controlled voltage source, or VCVS. Okay. For a voltage controlled voltage source, what that means is that the voltage being supplied by this source depends on a voltage elsewhere in the circuit. Okay. These are used practically to represent amplifier operation a lot. So if we have an amplifier that has what's called a gain of, say, 3, that means that an input voltage of 1 volt would generate an output voltage of 3 volts. Well, this voltage controlled voltage source kind of tells you what's going on to the output. So it's a way to represent an amplifier circuit. We'll get into that a lot more later. Our last potential voltage source that we'll see has the exact same symbol, but it's going to be described by R times IX. This is what's known as a current controlled voltage source. So I want to be very, very clear about this. In a current controlled voltage source, despite the fact that there's a current I there, this thing outputs a voltage, okay? So let's talk about the units of these scaling factors here for these dependent sources real quick. For a voltage controlled voltage source, the scaling factor K has units of volts per volts, or effectively it's a dimensionless quantity. So voltage in, voltage out, there's no transformation here. This term R converts a current to a voltage, which means R has to have units of volts per ampere, where volts is the unit of voltage and ampere is obviously the unit of current. These two on the right represent dependent sources. As I stated previously, all that means is that the voltage that's being supplied by these sources depends on either a voltage or current elsewhere in the circuit. Current controlled voltage sources are used a lot to model the behavior of transistors and things like that, which modeling transistors is beyond the scope of this class, but we do introduce the concept here for circuit analysis purposes. All right, so any questions on voltage before we move on to current? All right, nobody's saying. Yes, ma'am.
So for current controlled voltage sources, they only depend on a current somewhere else in the circuit, not voltage?
Correct. The current controlled voltage source depends on a current. A voltage controlled voltage source depends on a voltage. Right. Yeah. They both have the exact same symbol. a diamond with a plus and minus sign indicating the positive and negative polarity terminals. So you can tell which one it is by what the controlling variable is. So if it's the voltage depends on another voltage, it's a voltage controlled voltage source. If the voltage depends on a current, it's a current controlled voltage source.
And the current across the
No, it doesn't. It's in a DC circuit, it's fixed. So it just depends on what value the current has. So let's say that we had a current controlled voltage source that was, say, 5IX. Well, if IX came out to be half an amp, then the voltage would be 2.5 volts, full stop. But if the current changes, the voltage changes. It just depends on whatever the value of that current is. Any other questions? All right. So let's talk about current now. So fundamentally, current occurs because of charged particle movement, okay? Mathematically, current is defined as I as a function of time, I of t, is equal to the derivative of charge as a function of time, or with as a charge as a function of time with respect to time, right? This is very similar to what you guys saw in your engineering 120 series, where current was simply the amount of charge divided by the amount of time that the charge is moving. It's just a more formal description using calculus because we're big boys and girls now and we get to use calculus in this class, okay? Current can be defined verbally, I guess, as the time rate of change of charge flow in a system, which obviously makes sense because the derivative operation tells us what the rate of change is, right? Current is measured in amperes, where 1 ampere is 1 coulomb per 1 second, which I believe all of you probably already knew. So what I'm going to do now is I'm going to rearrange that expression for current. So the mathematical equation that we have here, I is equal to dq by dt, tells us what the current is dependent on what the behavior of the charge is. Well, sometimes we'll need the inverse of that relationship. We'll need to know the charge depending on what the current is doing. And that inverse relationship is Q is equal to the integral of I. And actually, I'm going to use dummy variables here. So I'm going to call this I of x dx. And the limits of my integration are going to be as such. I'm going to call this T naught to some later time t. And so what T naught represents is a time at which we know what the charge is. So it's an initial condition on the system. And what that requires us to do is to add a term, Q T naught, out here. Okay. So a couple of things. That Q of T naught is literally just a constant term that either has to be measured or it will be given to you in a problem. It is not inside the integral, okay? So if we have a current I of t, where this is t measured in seconds, and this is current measured in amps. So if we have a current waveform that looks something like this, call this 3 seconds, and this 5 seconds. And if we are told Q of 0 is equal to 4 coulombs, and let's say for the sake of argument that this is 2 amperes. If we wanted to know Q at, let's say, 1.5 seconds, how would we determine it? Area, right. Absolutely right. So the integral simply represents the area. So if we wanted Q at 1.5 seconds, this is 1.5 seconds. So we just want the area of that rectangle, right? Let's call this A1, which is representing the integral from 0 to 1.5 of I of t dt. What's that area? Not a trick question. 3 what? Three coulombs, 3 amps seconds, which is a coulomb. So is Q at 1.5 seconds 3 coulombs? No, because we didn't add the initial condition to it, right? So we know the area portion, but we have to add on that Q at T0 term. So this would be 3 coulombs, the results of our integration, plus 4 coulombs, which is our initial condition, would be 7 coulombs total. Okay, we cannot forget to add our initial condition. This level of calculus, area under simple geometric shapes like rectangles, squares, and triangles, is largely the level of calculus that I expect of you guys in this class. There are a few caveats. I expect you to know how to take the integral and derivative of an exponential function, and I will remind you of it practically every time that we do it anyway. And then also you're going to need to know how to do the integral and derivative of sine functions and cosine functions. That's literally all the calculus that you're going to need in this class. Simple sinusoids, exponential functions, and then remembering how to determine the area of triangles is one of the hardest things. 1/2 base times height. I'm telling you that because I had a section of circuits that I taught one summer, and over half the class literally could not remember how to take the area of a right triangle. So I'm not going to call anybody out. I'm just telling you what it is. 1/2 base times height. All right. So okay. So a current, much like a voltage, actually has 2 components to it. So if we had a generic circuit element A, and I said that there was a current of 2 amps flowing through it, again, we have an underdefined quantity, okay? So currents, voltages had magnitude and polarity. Currents have magnitude and direction. So I have to assign a direction to this current. So let's say arbitrarily that 2 amps of current is flowing down through the element. how much current would be flowing up through the element? -2 amps. So when we change the direction, we change the sign. Absolutely. You guys are catching on. It's wonderful. There's only one means by which to describe a current, and it's with a magnitude and an arrow indicating its direction. So let's move on to current sources in circuits. Our first current source will be a generic DC current source. So I could call this IS, like so. And so the magnitude of the current is given by the quantity IS, and the direction of the current is given by the arrow in the middle of that circle there. Then we have AC current sources, which are the exact same symbol, except there's a squiggle in the middle telling us that the current varies with time. These represent independent sources, which means they supply a fixed amount of current regardless of what is connected to them. So if we have a 5 amp current source, it's pushing 5 amps regardless if it's connected to a 1 ohm resistor or a 5 mega ohm resistor, pushing a particular amount of current. Over here to the right, we're going to talk about our dependent current sources. So this guy is what's going to be called a current controlled current source. And then over here, even further to the right, we are going to have a voltage controlled current source. Okay. Where these guys are our dependent sources, which means their value depends on quantities elsewhere in the circuit. The units on the coefficient K are amps per amps, and the unit on the coefficient G is amps per volt. So students quite often get voltage controlled current sources and current controlled voltage sources confused. And the reason that they get it confused is because you see a voltage Vx, and so you assume that that thing should be outputting a voltage. The key here, and this probably seems obvious to many of you, anytime the symbol has a plus and minus sign, it's a voltage source. Anytime the symbol has an arrow, it's a current source. That's it. That's how you tell the difference. It is that simple. All right, any questions regarding currents and current sources? All right, now we're going to talk about power and energy. We're almost done. All right, so power is mathematically defined as simply the product of current and voltage. Power is I times V. And for those of you I know that had Dr. Corbett in your 120 series, the handy mnemonic device here is I've got the power. So IV is equal to P. All right? Where power is measured in watts, where 1 watt is equal to 1 volt times 1 amp, which is the same as 1 joule per second. Power represents the rate of energy transfer in a circuit. Energy, which has a symbol of W, is simply the integral of power measured from one point in time of interest to a second point in time of interest. Just so we're clear here, we can have an alternative relationship for power. Power is the derivative of energy. And we will define energy to be the amount of power consumed over a fixed duration of time. All right. The topic that I'm going to talk about next, specifically related to power and energy, is what's called the passive sign convention, and it is one of the things that trips students up the most in this class. It's going to bite you in the butt the entire duration of this class, okay? So I'm going to try to explain it to you as succinctly as possible and as unconfusingly as possible as well. So let's say that we have a generic circuit element A, like so, over which there is a voltage drop, VA, positive polarity on top, negative polarity on bottom. Are we all okay with this definition here, okay? We just have a generic circuit element that has a voltage drop with a positive polarity on one terminal and a negative polarity on the other. If a current IA flows into the positive polarity terminal and out of the negative polarity terminal, we say that element A is absorbing PA is equal to IA times VA amount of power. Or alternatively, we can say that element A is supplying PA is equal to negative IA times VA amount of power. Okay? So it does not matter what sign the voltage VA or the current IA has. Okay, if the current is flowing into the positive polarity terminal, IA times VA gives us the amount of power that is absorbed. Negative IA times VA gives us the amount of power that is supplied. If we take that same element A, the voltage drop of VA over it. But now our current IA is flowing into the negative polarity terminal and out of the positive polarity terminal. We can say that element A is supplying PA is equal to IA times VA, and alternatively, element A is absorbing, write that in all caps like the other ones, PA is equal to negative IA times V. So to encapsulate this in literally just a couple of sentences, if the current is flowing into the positive polarity terminal, the element is considered to be absorbing power. If the current is flowing into the negative polarity terminal, the element is considered to be supplying power. Absorbed power is simply negative supplied power and vice versa. This doesn't seem like it should be particularly confusing. I would say more so that it's tedious. I'm just going to give you guys a heads up. On your in-class assignment here today and on several in-class assignments, homework assignments, and exam problems, you are going to be asked to calculate the power. You will pretty much always be asked to calculate either supplied power or absorbed power. On your multiple choice exams, I am telling you now, I am enough of a jerk. I am going to put both the positive numerical answer and the negative numerical answer because I expect you to know how to calculate which is supplied and which is absorbed. So you've been given fair warning that you need to be able to understand this. I'm for sure going to have to re-explain this again a couple of times, probably to people individually as they're working on different homework assignments, in-class assignments and things like that of, oh, Dr. Hartman, I did this and I got the wrong answer, but when I changed the sign, I got the right answer, or why? This is the answer literally 100% of the time, okay? So if any of this does not make sense, by all means, ask. I'm happy to explain it because you can lose literally letter grades on one of these multiple choice tests by screwing this one little thing up. Anybody care to ask a question? Yes. Okay, so fantastic question. So let's look at this top representation here, right? So the current IA, indicated by the direction, is flowing through the element like this. So it's entering into the positive terminal, goes through element A, and then flows out the negative terminal with the negative sign, right? The exact opposite situation is happening in the one below. The current is starting off here, so it flowed into the negative terminal, flows up through element A, turns left, and flows out the positive terminal. Does that make sense? Yeah. Somebody else had their hand raised. Same question? Yeah, no, that's an important distinction to understand, okay? And as you practice it more, it'll become more obvious. You won't have to draw something like that, but while you're getting used to it, absolutely draw a large line that follows the current through the element to figure things out. Not gonna hurt my feelings at all. Any other questions? All right. So let's work a quick example here, and then I will be quiet for the rest of the day. So let's say that we have the following circuit. I'm going to call this guy up here element 2. So that this guy down here is element 1. Here's element 3. Here's element 4. Here's element 5. And let's say that there is a 2-volt drop over element 1, positive polarity on top, an 8-volt drop over element 2, positive polarity on the right, a 10-volt drop over element 3, positive polarity on top, 10-volt drop over element 4, positive polarity on top, 10-volt drop over element 5, positive polarity on top. And let's say that element 1 has a current of 2 amps flowing up through it. Element 2 has a current of 2 amps flowing from left to right through it. Element 3 has a current of -4 amps flowing up through it. Excuse me, element 3 has -4 amps, yeah. Element 4 has a current of +5 amps flowing up through it. And finally, element 5 has a current of -3 amps flowing up through it. What I want us to find is simply the power absorbed by each of these elements. So for element 1, the current of 2 amps, is it flowing into the negative polarity terminal or the positive polarity terminal? Mr. Stubblefield, I believe. Yeah, for element 1. It's flowing into the negative polarity terminal, okay? So because the current is flowing into the negative polarity terminal, what is the power that's going to be absorbed? So I believe it'll be -4 watts. So when the current is flowing into the negative polarity terminal, absorbed power is -I times V, okay? So that's going to be -2 amps times 2 volts is 4 watts. Where that negative sign comes from the fact that we are calculating absorbed power, but the current is flowing into the negative polarity terminal, which means we need to add that negative sign. Solder, tell me what's going on with element 2. So it's obviously going to be 2 amps multiplied by 8 volts, but do I need the negative sign or not? I think that you do, because the current's flowing into the negative polarity terminal. All right, so I missed the negative sign there. -4 watts, -16 watts here. Garrison, help me out for element 3, please.
Is going to be negative.
Exactly right. So it'll be negative 4 amps times 10 volts. I made this far too boring or whatever because all of the currents are flowing into the negative polarity terminal. That's okay. So all of these are going to have a negative sign. I didn't think this through. That's okay. So that's going to be positive 40 watts. For element 4, we have a current of 5 amps, a voltage of 10 volts. But the current is flowing into the negative polarity terminal, so we need a negative sign since we're calculating absorbed power, which is going to give us 50 watts. And then finally, for element 5, we're going to have negative 3 amps times 10 volts is equal to negative 30 watts. Do me a favor and add all these together. Yeah, and then this one should be positive, so I just can't do math. Great. Thank you. Yeah. So I missed the negative sign on 4, and then I put one too many negative signs on 5. Yeah. Add all these together. Zero. This circuit is representing what's called Telegen's theorem. Okay, well, this is pretty much the only time I'm going to talk about it, but it should make sense. Okay. The amount of power that is absorbed in a circuit, or the amount of positive power absorbed, has to be equal to the amount of negative power absorbed. Or more simply, the amount of power that's absorbed in the circuit has to equal the amount of power being supplied to the circuit. It's the law of conservation of energy, right? So if we have 70 watts being absorbed, positive 70 watts being absorbed, there needs to be negative 70 watts being absorbed to cancel that out. All that's happening. All right, that is enough out of me for today. So we have 43 minutes remaining. There is an in-class assignment. There is also a lab. With that amount of time remaining, I guess choose your own adventure as to which one you want to take care of first. I will say there is a lab makeup day on May the 20th if you want to work on the in-class assignment. If you want to work on the lab instead, the in-class assignment isn't actually due until before class on Monday anyway. So you've got time to handle both.